So I'm here to talk about machine learning deployment from a little bit of a different perspective. So what I'm going to talk about is deploying deep learning models, neural networks, not the classical style of machine learning that you might have learned about in school. No decision trees, just neural networks. I'm not talking about integrating APIs because, calling a REST API is very easy. OpenAI makes it very easy for you as long as you give them a lot of money. That's not particularly hard. So I'm talking about deploying machine learning models on hardware, making them speedy, making them fast, compressing them. What kind of tools do you use for that? And I'm going to talk about all the challenges that are involved in bringing a machine learning model to production, from large language models to computer vision models. So I'm Tim. Currently I work in computer vision, but I have about a decade or more of experience with machine learning, with data, and I'm doing a very interesting assignment right now with computer vision, and I've worked a lot with this stuff. I've done a lot of experience with this, and I'm going to explain a little bit about how you can actually make this work. How do you bring a model to production, wherever it is? Is it on a drone, or is it on a GPU, or just run it on your crappy little old laptop? Well, let's see. Well, I'm going to talk a little bit about the software perspective. And, like any software, start simple, right? You start with the simplest thing that works. This is PyTorch. Maybe just a quick question. How many people have worked a little bit with PyTorch? Okay, I see one hand, I see two hands. I see a few hesitant hands. So, you have a few large deep learning, machine learning training frameworks, that you can use to build these models, from large language models, etc. This is, a very basic, simple example of a machine learning model. Machine learning model is basically a function, right? So machine learning is, at its core, is function optimization. I heard something about simulating neurons. It started like that. It's not really simulating a human brain. Not really. It's more function optimization. What you do is you create a function, and you create a function that you can think can actually solve your problem, as long as it has the right parameters. So, we create a model, we create a function. This is a super simple function. This only has 3 layers. This is basically, the type of neural network that you learn in school. Just a 3-layer perceptron. You have a few linear, fully connected layers, activation functions in between, sigmoid at the end, and as long as you make a function that you can think, if it has the right parameters, it can calculate your answer, right? That's the whole idea. And then you use your data. Then you have a data set, a labeled data set, and you use that data set to tune your model to pick the right parameters so it can solve your problem. You use a loss function for that to determine how far away are you. Does anyone know what a loss function is? Just to get a bit of a feel for the level here. No one? Okay. Yeah, okay. So what the loss function does, it basically tells you how far away are you from how far away is the model from solving the problem. So you have a labeled data set. The loss function basically tells you, okay, we have a target. This is what it should be. And the model actually, okay, so for example, we have a cat or dog classifier with a lot of pictures as input and labels as output. And at the start, the model tells you, oh, these are all cats. Then the loss function says, okay, that's completely wrong. Then we use our training to optimize the loss function. So it's basically function optimization. I'm not going to go too deep into this, but to just give you a little bit of a background about where you start. So we start with a trained model, and these models are usually trained in frameworks like these, like PyTorch or JAX or TensorFlow, where you create a model, you train it, and okay, then we've trained it. Now we want to move to production. Like all the developers, it has to run on a different machine. The job is not done if it runs on your machine. It also has to run on a different machine. So how do we do that? Well, let's start simple. We've trained our model. So we save all our parameters to a state file, to a model.pt, PyTorch, and then we load it again on a different machine. So we reinitialize the model code, we load the checkpoint, we load the parameters that we've trained into the model, and then we plug in some input and it gives us the right answer. Are we done? Well, if this works for you, then you're done, right? We're writing software. If you solve the problem and you solve it in a simple way, you're done. But it's not always, that simple. So if you're working in a business, you might have a lot of different requirements. Things like, I want to run it somewhere else. I want to run it on a drone. I want to run it in my 100 GPU, $1 million data center. I want to run it on a phone. Or I want to run it on a custom chipset. I just trained my model. How am I going to get it to something like this, right? I want to use a different backend language, right? All machine learning right now is done in Python mostly. Maybe some other languages. Python is a crappy backend language, in my opinion. I write it, but it fucking sucks. I want to use something different. I want to use Scala or C# or whatever. I want to use a different backend language. You're deploying it to some sort of environment, hardware. You might want to optimize it. It needs to be fast. It needs to. You don't want. So if I end up with a 13 billion parameter model, I have to download multiple gigabytes to get it up and running. Is that acceptable? So you might want a fast model. You might want a small model. GPUs have limited amount of memory. You can't just chug in a 13 billion parameter model on any kind of hardware. So you might want to do some optimization there. And of course, dependency size is an issue. For example, you have the CUDA library, and you have TensorRT, and you might those are very commonly used libraries. They also are like 3-4 gigabytes of dependencies that you chug in. If you use your training framework, they're even bigger. They have to support that so many hardware, so many API calls. I don't actually know why it's multiple gigabytes. NVIDIA will know. But yeah, dependency size is a big issue. If you want to just run your model in a programming language, you don't want to download multiple gigabytes of shit, usually. So yeah. So there are, if you're deploying machine learning models, you have like a huge toolbox of things that you need to get it running to production, right? So you can do it simple, but if you have more complex use cases, you're gonna want to pick and choose what kind of direction you want to go in. So that's why I start from requirements, because if you want to deploy to a mobile phone, you're going to pick a very different kind of route through the environment than if you're going to deploy on a GPU, for example. So it very much depends on where you want to run your model on, and that comes with what kind of tooling you want to pick. So the journey always starts with your machine learning framework. Either you're downloading something from the internet, and then it's written in PyTorch or JAX, or you're writing something yourself, then you're also using something like that. So the journey always starts with your machine learning framework. And your machine learning framework can, by the way, usually also do all the other stuff. So if you want to just run inference, like I said, with Start Simple, the framework you trained your model in can usually also do inference. It's not the most suited for it, but if you just want to solve the problem simply, just use the framework the model is written in. That works. If you have more complex use cases, or you want to reduce your dependency size, or you don't want to use Python, you might want to do something different. So usually what you do is you export your model from your machine learning framework. Then you have your model format. Your model format can be run in an inference runtime, right? So you have some sort of library or runtime which you can use to actually run your model. Usually you have very primitive runtimes, and usually you have some microservice or cloud abstractions surrounding that. Things like semantic kernel, like you mentioned before, fall under that kind of thing. So I'm not going to talk about the microservice and cloud abstractions, but I'm going to talk about the runtimes that are usually used under the hood to get a bit more feel how you would do the deployment yourself. Usually if you're on Azure or AWS, they offer you their own inference services, but you do pay for that. So if you want to handle this case simply, just use some sort of cloud abstraction, that works. I'm going to talk about how you're going to do it yourself. Otherwise, it's not going to be much of a talk if I just say, okay, just deploy it on Azure and you're done. You can do that, but I'm not going to talk about that here. Usually have some layer with hardware acceleration abstraction. So things like CUDA, OpenVINO. We're going to talk about that a little more later. You need some way to abstract the hardware. Usually the inference runtime supports multiple types of these layers, and you have your hardware itself. So you want to deploy on a GPU, an ASIC, CPU, FGPA, a mobile, IoT, whatever. Right, so yeah, sorry. I'm just going to give a quick overview to give everyone a bit of a feel what is out there. So like I said, we start with machine learning frameworks, PyTorch, TensorFlow, JAX. Those are the big ones right now. Those frameworks can export their models from those frameworks, so you can have your model in a format that you can move anywhere, or at least anywhere there's support for. So there are some training framework specific formats like TorchScript, TensorFlow, TensorFlow Lite, CoreMLs, for example, for mobile. OpenVINO is an Intel-related format. ONNX, I'm going to talk a little bit more about that later, is very device independent, very general. So once you have your model format, you might want to use it in an inference runtime. And like I said, training frameworks are usually also decent inference runtimes. The disadvantage is a little bit that the dependency size is very huge, and sometimes it doesn't really support the hardware that you need. So you can't go everywhere with just using libtorch or TensorFlow. ONNX, I'm going to talk a little bit about it later, is a Microsoft framework, very general. OpenVINO is from Intel, TensorRT from NVIDIA, TF Lite. You also have model-specific runtimes. So whenever you get a very top of the line new style of model, like large language models, like generative AI, you get the problem that general machine learning inference frameworks don't support all the features that you need, specific quantization formats, specific types of optimization. So usually when there's new models, we saw that a few years back with YOLO style models that were written manually, you will get model-specific runtimes that are good at running very specific models, like large language models, or like running specific types of generative AI. So those are separate types of inference runtimes that are a little bit more specific to specific tasks, but they're better at it. So usually if you want to run a large language model, if you want to run it in the fastest way possible, with the best optimizations, you're going to pick a large language specific runtime instead of using very general runtimes like ONNX, just because it supports more optimizations, hardware abstractions. So NVIDIA, AMD also has its own platform. OpenVINO is for CPUs. You also have platforms for cloud tensor accelerators. And then, of course, the hardware. I'm going to talk a little bit more about that later. So we have GPUs, ASICs. Going to explain a little bit what ASICs precisely are, and the CPUs. So basically, if you want to, So basically, what is out there is a very large set of tools. You need to find your own type of journey to specifically deploy what you want. So yeah, it's a little bit of a mess out here. You see, it's a bit of a mess, but you know, yeah. So how do you find your way into this mess? So, like I said, start from your requirements. So you either want to run something on hardware, so you start at the bottom, or you have a very specific type of model that you want to run, right? So you either start here. Okay, I have a GPU and I want to run models on it. What does it support? Okay, so for example, if you start with NVIDIA, you might want to see what type of hardware abstraction is out there, which inference runtimes support it. If you want to start on mobile, you want to start with a mobile specific type of framework. So yeah, it's a little bit of a mess out there. It reminds me of JavaScript like 10 years ago, where you had like a framework every 6 months, right?
Every 2-3 months.
Every 2-3 months, something like that. So it's a bit of, you need a bit of pathfinding out there to find the right solution for yourself, right? And there's so many types of models and requirements. So yeah, I'm trying to give a little bit of an overview, but it's still a bit of a mess. And you know, maybe in 10 years it's better, but you know, now it's still quite messy. So you want to start from your requirements. So either the hardware that you have, so you want to run it on a drone or a specific type of GPU, or you want to start with the model and see what kind of options there are. So you want to plot your way through things. So ONNX, I'm going to show that a little later. It's a very good default option because it supports most machine learning frameworks and hardware. So if you want a good default option, and if you have a lot of models that are in, you know, you want to bring in production, so sometimes I have like 10 or 15 types of production style models. ONNX is a very good general format because you can deploy it anywhere, and any type of machine learning framework supports exporting it. So this is a Microsoft framework. I'm going to demo it a little later, but it's the default option. If you need a model that requires cutting-edge features, custom operators, quantization types, a large number of parameters, you might want to consider model-specific runtime, because then you're typically using a large language model or generative AI. And you might need the little bit of extra speed that you get from a model-specific runtime. Same thing with small, specialized, exotic hardware. mobile, ASICs, start from the hardware abstraction layer and see what kind of stuff is supported from there. So it's, you have to plot your own journey through the whole set of tools. And like I said, using your machine learning framework as a runtime is possible, but the dependency size is very large. So if you use PyTorch, it grabs like a huge number of layers. It's like JavaScript that you suddenly end up like with large and many dependencies. You're stuck with Python. There are some, you can use PyTorch from other languages, but from my experience, it's a little unstable. So you're stuck with Python. Nah. So yeah, let's start talking about the model format. So when you train a model, they exist in two different parts, right? So you have a set of weights. Those are tensors, multi-dimensional arrays, essentially, right? So if I'm talking about a 7 billion parameter model, then you have 7 billion numbers that are being stored in your model format. So let's say that we're using floating point 32. So multiply by 32 bits or 4 bytes. And then you get the size of your model as a file, right? Very simple. You also have the code. So if you remember the code from the first slide, models are basically, usually if you build a model, it's a little bit like functional programming, right? So you don't have, usually you don't have internal state mutations. It's a pure function from input to output. Well, I think I cut away the output here, but you get the you get the picture, right? So it's a functional. It's basically a functional program, and that program uses in these operators. It uses the weights that you've stored. So basically, when you're deploying a model, unless you want to, pull the code in some other way, you usually want some way to transfer the code with it. So you don't need to translate the Python code into C++ just to use the weights. So yeah, let's talk about the weights. They're n-dimensional model tensors. You can use, just see them as arrays, basically, right? So they're multi-dimensional arrays. In machine learning, we call them tensors. And when I started learning machine learning, I grabbed a book of tensor algebra because I thought that would be useful, but it isn't. What you only need is linear algebra, and they're basically just multi-dimensional tensors, arrays. You can have a bit of weight compression or quantization being supported in these formats. Sometimes you can have sparse weights. We'll talk a little bit later more about that. Or you can quantize the weights. And it depends a little on the model format exactly what is supported. So the code. Right, so like I said, you don't want to rewrite your Python code in Java or C++, right? So you want to ship it in some way in your model format. That means you have to export it as well. Because it's functional code, you can export it. I think the export format I like the most is a model graph, right? So you have a functional model graph, you have input, and each operator basically takes the input, transforms it, and gives it to the subsequent operators. And you have this whole computation graph, and in the end it generates your output. And all these operators are hooked up to the weights. So basically, this is ideal. If you can compile it to a computation graph, it's for the best. It's also a little easier to optimize. Alternative is jet compilation. So torch script, torch compile. They use some sort of just-in-time compilation. It's usually what happens is that they have a JIT variant, so just-in-time language for Python. So this is basically Python being ported into a JIT kind of format. So it's basically a full programming language, and you compile it to bytecode. You can do this, it works. I find it a little harder to debug and to manipulate, but it's very possible. So it's an optional part of the model format. You can also just write the code out, but that means you might have to translate Python code to whatever language you're deploying in. So one nice thing I want to mention is that if you have everything in graphs, then they're just data, right? So graph manipulation, if you want to manipulate the computation graph of your model, it's a very common step in deployment. You might find out, for example, that not all operators that you exported are supported by the hardware or your inference runtime. So, for example, you can cut away parts of the graph and execute it on the CPU. So you can cut your model in half and execute part on the CPU. You could also add steps. So for example, if you're pre-processing, you want to move that to the GPU, or you just add it to the computation graph. Very simple, makes deployment a lot easier. You might find out that specific operators are not supported by your hardware. So a very common step is also to replace operators by supported versions. One thing I encountered, for example, is, for example, I do computer vision. So one case I encountered is that there was an operator that resized images, and there were very specific options that were not supported. So I just replaced it with a different operator, a manual implementation that worked. If you do stuff like that, remember to revalidate your model. So if you change the model, even in very small ways, revalidate it, because small changes can sometimes have unexpected consequences. You can also cut it in multiple pieces. And the nice thing about graph manipulation is that there are optimizers available. So there are a lot of small optimizer libraries that do things like operator fusion, very common optimizations, and that can speed up your model a bit. Just look at optimizers for your specific model format. For ONNX, there are quite a few available simplifiers, optimizers. Yeah, so let's talk about hardware. So first of all, CPUs, widely available, usually compared to GPUs, pretty cheap. And you have to remember that we have modern instruction sets like SEMD, AMX. You can vectorize a lot of stuff. So actually, you don't really need a GPU to execute models anymore. So CPUs, even for large models, I'll show it later, are doable if you want to go for cheap and easy solutions. So it works best for either small models or very large models, because usually with large models you run into memory limitations for your GPUs. You need very expensive hardware. So and RAM for a CPU is very cheap compared to GPUs. So either small models, because they're very quick, even on CPUs, or very large models, because then you can bypass memory limitations very easily. Actually, I want to do the GPU first, because I think it will provide a little bit of context. So GPUs, what are they? So highly parallel hardware, very good for working on large data sets at once. So, originally made for graphics, but now they're used for accelerating basically anything. So what GPUs have is a large shared memory bank. And besides that, they have a lot of different computation cores. So this is the NVIDIA H100 video card layout. It's a little small, but they have large shared memory banks, and each computation unit has its own memory as well. So you have a memory hierarchy. So you have one large bit of shared memory, and then you have a lot of computation units that can work very much in parallel. So you have thousands of threads working on this thing, and a lot of cores to basically process large data sets all at once. It's not particularly energy efficient. For NVIDIA, for example, you have very different core types. So you have the CUDA cores, maybe a little bit of a misnomer. Those were usually originally meant for shaders. They're also called streaming cores. They're very general. They have a lot of threads. You have tensor cores. They're very good for matrix and accumulation. Very good for most machine learning. You also have ray tracing cores, and we don't really use those. Those are used for graphics features. ASICs. So basically, at the start, most machine learning models were run on GPUs, right? And what happened is that it turns out GPUs are very expensive, not very particularly energy efficient, and they're meant for graphics originally, so you get a lot of crap with it that you don't really need for machine learning. And we talked earlier about the tensor cores, so they're very good for matrix operations. Basically, you could see as machine learning ASICs, application-specific integrated circuits, right? That's an ASIC. They're basically custom built for accelerating machine learning workloads. So most cloud providers have one, Google has one, Amazon has one, Azure is developing one, I think. They have good memory bandwidth, they're more energy efficient. They're also a little less general, so very exotic operators are harder to support on them. So you have a lot of stuff available. Google's TPUs are very well known, but you also have stuff from AWS, AMD, IBM. They're very good at matrix and machine learning related stuff, but not much else. Google has a very nice TPU paper. Currently Google doesn't publicize a lot, but back in 2016 they wrote a very nice paper on the first TPU they actually made. So in data center performance analysis of a tensor processing unit is the paper. They published a lot of the inner details about how these types of tensor cores actually work, how they accelerate matrix operations. If you're curious, you can read that paper. Got the diagram from there. So basically, they have these square shapes of memory, and they can very quickly have some operators around that are very quick in multiplying matrices and doing a lot of the tensor operations. And it's basically also how the tensor cores on NVIDIA probably work. But the trick with hardware companies is that they don't really publicize their stuff, right? So you don't really know how it works, but Google sometimes Google has some nice papers on it. So if you want to know a little bit about how it works, just start reading. So just to illustrate the difference a little. So this is how you, for example, add two matrices on a CPU, right? So just a for loop. If you're lucky, this will get factorized. If your compiler is smart enough, this will get factorized, and it will take steps of like a few hundred integers at the same time. It will just use one instruction to add all of these. Usually compilers are smart enough. This is a CUDA example. So basically what you define a kernel here that will give references to the different types of matrices that are out there, and then you can just do the addition, and then you start a kernel with a number of threads, and then it does the addition. So basically, usually the limit is about 1,024 threads or something like that. That's pretty typical. So if you have a typical CPU, if you have a very good CPU, you might have like 32 or 64 threads at the same time, right? Well, on the GPU, it's a few factors above that. If you want to, it's a little on the low side here, but you can just about read it. If you want to use a tensor core, you can use the GEM API, which is generalized matrix multiplication through CUDA, and then you're using the tensor core, and then it's one operation. So then you don't use 1,000 threads, then you use one TOC to do a matrix operation. So then it's even more efficient. So that's basically, you know, to get a bit of a feel what the difference is between the hardware. This is still pretty efficient if it gets factorized. So don't despair if you're not using one of these fancier chipsets. Demo time. Okay, so I wanted to show a few of these runtimes and to show you how we can get this working. So how are we on time? Okay, about halfway. Right, so ONNX is very, very general. So ONNX can basically export from any trading framework. So I wanted to just demonstrate this first. So here we have our model again. And basically it's very simple. If you want to export it, you just give the model, you give it a bit of sample input, and it writes away the model file. You have an offset version, which is basically, there are different standards for ONNX. So ONNX is very disciplined in versioning their schema, basically. So you might have inference runtimes that support up to offset version X, etc. You can give it some standard. Constant folding is an optimization that you give, and you can name the inputs and outputs. So yeah. Okay, well, it's not particularly exciting, but now we have our model file. So let's first see what we actually exported. So usually, the nice thing about these model files is there are actually very good visualizers available. So Netron is very nice in that you can actually see the computation graph. Okay, why isn't... Okay, I'm seeing it here, but not here. Okay. It's a little confusing. Okay, so here you can see the computation graph of the very simple model that we just exported. So like you see, it actually matches the code that we just had, like it's just a multi-layer perceptron, right? And the nice thing here about this is this visualizer makes it very easy to get a bit of insight in the model, and also, you know, you can see, okay, if I want to move this part to the GPU, I just cut it here. It gives a bit of insight on what you're actually deploying. And the thing about ONNX is you can deploy it anywhere. So there are WebAssembly runners, right? I'm not going to demo that here, but you can just, if you have a large language model in ONNX, you can just put it on the web and just run it on your phone. Okay, your phone will overheat probably a little, but it's all possible. It will use WebGL, so it will use your GPU to accelerate these types of things. I don't really have time to demo that all here, but just know that it's available. So, yeah, like I said, it's really an export step. You take your model, you train it, you export it. And then you can use a separate runtime as inference. So we have a separate runtime, and this runtime is a lot, it's not as big as PyTorch, and it supports a lot more hardware than PyTorch. So ONNX is nice. If you want to run it on your phone, you can do that. If you want on the web, on your NVIDIA card, it supports, I think, dozens of hardware platforms. So this is the default option if you just want to pick something. If you don't know what to pick ONNX, you're usually good. So let's do some inference. So this is basically a binary classification model, right? So the output is a single number. So I just want to do something simple. So let's do some ONNX inference. Okay, I'm getting my number. Yeah, let's open. So it's very simple. Here's the code, right? I load my model. I run my session with input, and this time I'm just using randomly generated input because I didn't really train my model, so it doesn't really matter all that much. The model is exported as float32, so I have to cast it to float32, and then I just get the output. And this is basically as simple as it can get. And you can do this basically anywhere. Most programming languages have an ONNX library, and you can basically deploy this anywhere. So this is an excellent default option if you just want to do something simple and portable. Let's do something entirely different now. So we have a different, entirely different type of model that large language models are supported by ONNX, but you have to remember that some of the more exotic quantification options in combination with operators are not always supported, so you might not get the fastest version right now. I imagine it will change in the future, but right now, the best option for large language models is usually, no. I have to activate it, so I hate Conda. Okay, so I downloaded a Llama checkpoint, a 7 billion Llama checkpoint. And you have to remember, this is a 2017 laptop. It's very crappy. It doesn't support much. And you would think that if I run a very big large language model with 7 billion parameters, it would catch flame. It still might, but I'm gonna do it anyway. So yeah, let's do this. So what we're demoing here is Llama CPP, a large language model inference runtime. It can run more than just Llama. It can run a lot of different large language models. It started with Llama, so it's called Llama CPP. But there are a lot of large language models supported by it. It uses, I suspect this is a Facebook model format, GGUF. It's actually a few months old. So this is a very new style. That's why I didn't have it in my presentation yet. It's a very new model format. Like I said, a new framework every few months. So we're loading this Llama checkpoint, and it's a 7 billion parameter checkpoint. So let's see how large it is. I actually don't know. Ooh. Why is it only? Yeah, so it's almost 7 gigs that you're downloading in just a checkpoint, and this is not the largest checkpoint that you can download for Llama. So you need a pretty beefy GPU to run this, because you're not only loading the model, but you're also loading the input tensors. So it's not just the model. You need to load the model and then run computation on it. So you quickly, for modern GPUs, this is just about doable. If you run a larger checkpoint, you quickly run out of memory. This laptop doesn't have anything, so just CPU. So let's see if I can run this prompt. And I just want to ask a question. Name the planets in the solar system. And just like the demo here, there are a few parameters, etc. And yeah, let's see how this goes. So like you see, it loads all the layers. It's a model that has 290 different types of operators and layers in it. So that's pretty nice. It looks like my CPU isn't supporting all instruction sets. So AVX 512 is not supported here. So it will be a little slower. But let's see what's... It ran yesterday, so if my laptop catches on fire because of this, then yeah, let's wait a little until we get output. I really am curious about the planets in the solar system.
It will be just character by character.
It does the whole thing at once, and because it's probabilistic, Sometimes the output is a little larger and you have a stop token, right? So you have this stop token, and once it generates a stop token, then it stops generating stuff. Yesterday it finished in like 20 seconds. Maybe because my charger is not in.
It's throttling this mic.
Yeah. Okay, let's look back later. I'm sure once I finish a few slides, then we'll have finished this demo. So let's go back to the slides, and in a few slides, it will probably have finished the prompt. So the nice thing about it actually makes this type of stuff possible, even on crappy old hardware. So, like you see, optimization can be pretty important, right? CPU is possible, but if you have super large models, you'll get an answer, but you might not get it very quickly. Yeah, so let's start talking about optimization. So let's start with this. There's no best model, right? If you're talking about the best large language model, there's a best model for a given speed and size. So if you want to deploy something on specific hardware platforms, you need to first determine how fast does it need to go, what kind of hardware can you afford. If you want to buy one of NVIDIA's 20K video cards, well, not everyone has that budget, especially if you want to use that video card in a lot of different locations or a lot of different VMs. So, like I said earlier, model size is number of parameters times the parameter size. Larger models take more memory. There are a few ways to measure speed in a model. So you have gigaflops. I'm assuming everyone knows what a flop is, a floating point operation, right? You also have gmach. This is a little bit more common. If you're looking at things like tensor core, matrix multiplication is one operation. So you're not counting in floating point operations anymore. You measure the model performance in gmachs. How many tensor operations do you need, right? So even gmachs are an estimate. Measurement is always key, like all benchmarking. You might have memory bandwidth issues, bottlenecks in your model, you know, like the tunnels where everything keeps waiting for one operator, bad optimizations. Use tooling to benchmark. NVIDIA has good tooling. Start with calculating your performance budget, right? So if you want to bring a model to production and know exactly what you can do before you bring something to production. If you want to bring a large language model to production, can you afford to buy a super large GPU, or do you want to run it on your phone? Very different types of calculations. How fast do you want your answer? So first your performance budget, then your model. You have different types of optimizations. You have size optimizations. A smaller model fits the hardware easier, usually executes also faster, might require some loss in precision, might want to do speed optimizations. Same exact model, but faster. Scale up, scale out. Everyone knows that. If you're training your model, remember that model size is a hyperparameter. Number of layers, tensor dimensions, pick the smallest that works. Start thinking about this early in the training process because it's more expensive later. And use your framework's built-in optimizers as a first step. Let's see if my large language model actually finished. Should be. Oh, it generated a lot of tokens. It wrote a whole essay on our solar system. It didn't do that last time. That's the problem with probabilistic models. So I think it wrote a whole essay on our solar system. It's lucky that I plugged in my battery before, so I still have, but so that's why it took a little longer. Last time I tried it, it answered with one small sentence. This time a whole essay. That's the problem with large language models, I guess. You never know what you get. But, well, you see the idea, right? Okay, let's move on with the presentation. So first, oh crap. Okay, then I only do the quantization. I'll rush through this. So, yeah, this is a fucking shame. I need more time. Okay, give me 10 minutes and then I can finish the quantization demo. And then I'll skip the other. Okay, so parameter size, right? So everyone knows their floating point formats a little bit, right? You're developers. So does anyone not know how a floating point works? Okay. So floating points are two parts. You have the exponent and the fraction. The exponent determines the dynamic range of the floating point. How high can it go? Can you go into the millions or into the billions? So if you have a larger exponent, then your number can get larger, or basically the range of the number explodes. And the fraction is for the precision part of the floating point, roughly. So if you run your model, you can have floating point 60, you can have FP32. You'll also have something developed by Google called brain float. And the idea behind this is basically that for modern machine learning operations, the dynamic range is a lot more important than the precision. So what it does is it shortens the fraction part of the floating point and expands the exponent. That's the basic idea behind brain float. If you have hardware support for this, this is very nice as an option. So quantization is basically, I'm going to go through this a little fast. Basically, so if we want to reduce the size of the parameter, that gives us an exponential speed up, right? So if you go from 4 bytes to 1 byte for a parameter, that means you cut your model size in 4, and you also speed up your model size all at once. So smaller parameters help a lot. For int quantization, basically what you do is you map, you tune on a data set, you see what kind of values the float can take, and you map that range of your floating point to an integer. So basically you change your number type to an integer, and you have a specific mapping parameter, a 0 point and a scale, so that you can map this continuous range of floating points to an integer in a way that you can still do matrix multiplication operations on it and still get a decent answer. You have reduced precision with this, right? And because it's the easiest option, this is basically the most frequently used model optimization. There are different types available, so FP32, 16, brain float, FP8, int 8 is quantized, FP4, an option where a lot of research ongoing here, so very small floating point parameters are also part of research. We'll see that in a few years in hardware, I think. Very promising option. You even have int1 quantizations. They're a little less useful, but so yeah. I might skip this a little, so you have different types of quantization strategies. I'm not going to do this whole slide, so the most important part are quantization after your training or during your training. If you do during your training, if you do quantization aware training, you get better precision, but it costs a lot with training computation. You can also do it after the training, but you get a little less precision. So this is basically the last part that I actually want to do. Then there are a few other optimizations, but yeah, we can't get to everything, I guess. Oh. So what we have here is I have my Google Edge TPU. This is a chip that you can, a very small tensor core basically, an ASIC. So a small chip which you can use in a drone or a camera or a small device. Android's neural core is apparently a variant for that, so I have a variant for that in my phone. So if you have a neural core processor, it's a variant of this type of thing. I actually don't recommend this chipset because it kind of looks like Google is abandoning it. In typical Google style, it's probably $100 million business, but it's not $1 billion business. So they're not putting a lot of time in this. But it's a good example of deploying a model on hardware, right? So yeah, let's, where's my, so here. So the first step is that we start again with the model. And this time we're quantizing the model. So we're moving the model to int 8, so a smaller parameter size. Usually what you do is you have a data set that you can use to tune this quantization, to determine the optimal quantization parameters. It looks at your model execution. This time we're just randomly generating normal numbers, right? This is just an example, but typically what you have is a data set which you can iterate through and which can be used to quantize your model. So what we're going to do is we have this model defined here, just this time in TensorFlow, because we're exporting to TF-Lite. TF-Lite is a very mobile-friendly format, and TF-Lite is also often used as an in-between format for chips like these. So you basically do a bit of model formatting, hopping. You first go to TF-Lite and then you export it to your specific chipset specific format. So here we're gonna do post-training quantization. So after the model is trained, we're gonna quantize it with a tuning data set. So let's switch environment. So first what we need to do is export the model. And that's not this one, that's... So we export the model from TensorFlow and we use quantization, right? So now we have our model. I'm not gonna show it in Netron, but you can look at it yourself if you want. You can visualize TF-Lite in the same way that we visualized ONX. You get a similar representation. Now the next step is to compile the model. So we have my model.tf-lite. We're going to compile it to Edge TPU format, to an Edge TPU format. And now I have my Edge TPU. Oh, what is going on here?
HDMI when you touch
I touched the HDMI. Oh no. Now I'm gonna TF-Lite. And now I'm going to use this chipset to run my model. And the answer is -1. It's super exciting, I know. But this is something you can basically put in a drone and run computer vision models on this. It's the same type of chip that's on your phone. And Google is abandoning it. It's a very neat type of thing, but it's a little out of date. They haven't done an update in, I think, more than a year. So I think Google might be abandoning it. Or they might pick it up again due to the AI hype. I don't know. You never know with Google. Don't invest in Google shit. They do weird shit stuff like this. So yeah. So basically, it's to go to a smaller chip. You do quantization. You do a bit of model hopping. So you convert it between different types of model formats. And then you end up on this thing. And this is a USB style format, so it's a little slower, but you have practical stuff that you can just plug in as a card in your device. Okay, so let's go through the last bits a little faster. Right, so there's also sparsification pruning during training. You can read the paper. Model distillation, also very interesting. I'm going to do this very quickly, sorry. So what you basically have is you have a very large, for example, a teacher model, and you want to knowledge transfer that to a smaller model for inference. So this is something that's also used a lot with large language models. You have a lot of distilled versions of models. And the thing is that you don't really need a labeled data set for this, and you can use parameter copying to speed up this process. You retrain the model on a smaller, with less layers or less parameters, right? And what you can also do is specialize the model. So if you have a ChatGPT style model and you only want to do it for coding, then you only feed it coding related things during this knowledge transfer. So it's a very flexible type of thing to make the model smaller and faster. Yeah, I would say we're running out of time, so read the paper, knowledge distillation survey, explains all about this. I don't have the time anymore. Sorry, guys. Upscaling, outscaling, I think that's yeah, you can distribute models on different GPUs or yeah, split a model through different, yeah. I'm just going to skip this. I think scale up, scale out is, you know, something most developers will know. Some final thoughts. So, you know, ML ops as a field is very much still in development, very fragmented. Like I said, it feels like web development 5 years ago, a new framework every few months. So a lot of the state-of-the-art models are still written manually with CUDA kernels, etc. Some general hope for the future is, you know, a focus on more standardized core tooling and core formats, and less spending my life working with duct tape Python libraries and CUDA kernels. And we need better hardware extraction. So things like virtual memory swap, portable APIs. Right now, NVIDIA is the king, you know, but it shouldn't stay that way. We need more portability. Questions?